So hi all, welcome to the Samurais Cache Design Workshop. So I am Noman Akbar and we'll be looking into the cache design for today. Let me first discuss the agenda items for today. Then we'll deep dive into each item. So what will we be covering today? So let's discuss today's agenda. So first point that we will be discussing is that why caches exist, right? What is the need for the caches? So why caches exist in the first place? So that we will be the same point that what is the need for the caches actually is. Then from that point we will go directly to the cache organization, that how the caches are organized and how the address, actually the memory address you gave it. So how does that translate to uh, caches and how that cache address decompose, right? So cache organization, and after that cache organization, in which we'll mostly cover the direct map caches. Okay, so direct map caches, and in the first point, and, or you could call it the module 2. Okay. So in the third part of the third module, we will have our first lab, which will be designing the direct map cache in system Verilog. Okay. So lab 1 will be that we will design a direct map cache in, and then we will definitely have a break here for about 15 to 20 minutes of break after designing this, and you will design along with us. So right, so be prepared with your laptops and the EDA playground uh, on. Okay. So after the break, we will start with the associative caches. Uh, So okay, so set associative caches. Uh, Set associative caches, and so this will be like fourth item maybe, and then we'll go to different types of like policies, replacement policies. So how those replacement policies work, and why are they needed in the first place. And we'll also be looking from the hardware perspective well for all of these, we could say, concepts. Okay, so then we will be covering the write policies, write back or the write to, or how does the cache and the memory interact together. Okay. So 6.1 will be the write policies, and then we will cover our main, you could say, lab today, which will be the lab 2, which is designing set associative cache with LRU replacement policy. Okay, so this will be our uh, lab 2 for the day, in which we will design the set four-way set associative cache, or it can be parameterized as well. So with LRU policy replacement uh, in system Verilog, along with the test branches, and along with all of the coding stuff. So all of those who have registered for the paid tiers, they will be provided the memory model and the test benches along with these uh, coded designs in our lab as well, so that you have a full design to uh, go to run and simulate that. And okay, so let's get to the first agenda item for today. Questions before starting the first item? So let's start that what is the need actually for why caches? Okay, so we all know that usually the CPUs or the processors, So let's assume this scenario. So there is a processor which has to communicate with a memory, right? Main memory kind of a thing. So this is the memory because data that this processor needs resides in the main memory, and processor doesn't have enough memory to have actually um, have got all of the data inside the processor and to reside it inside the processor. So it has to fetch data from memory and again send it to the memory, right? So, but the issue is this main memory, which is like DRAM based. Okay, so it will take, for example, 200 cycles to complete a single transaction. 200 clock cycles. Let's assume that. So maybe in modern computer architectures, it would take maybe more or less. So let's take this number. So it will take like 200 cycles. Okay. So now imagine you are running a code which is, for example, is like this. For you have a code, okay, I equals to 0, then 1000, like plus plus, and you are just adding some array. Okay. For example, this was your code that you want to run on that processor. So what will happen is that you now need, so now this array of I resides in this memory, right? So it resides in this memory. So let's assume the code, which is like you have to run it like for 1000 times, right? So it means without those caches, you have to go to the main memory actually for 1000 times, like, okay. So even resolving this array with this loop, so you could imagine even 200 cycles cost 1000, right? And you have codes with like many of these loops, right? In real workloads or in real kind of programs, you have a lot of these. Oh, okay, so now why we use DRAM or why can't we use a very faster memory? Because main memory needs to be like a larger one, right? So it has to have a more capacity. But the DRAM is really, you could say, in caches mostly uses the SRAMs. So if we compare SRAMs or the DRAMs, SRAMs are more expensive. They are faster, but they are more expensive. So building a main memory using an SRAM memory will be like really a costly thing, and it will not make the processors or the hardware feasible, right, in terms of cost. So that's why we build a memory using the DRAM technology uh, and have a larger like memory space there so that we can store more data there. Okay. So this slowness of the memory really becomes the bottleneck, right? So ideally, maybe the processor wants to complete one instruction per cycle, maybe. Okay, let's target that. So now assume you have a 200 cycles of store going on, right? So you have now a dependency on that load. Uh, for example, if instruction needs that, so it needs to stall, right, for that much number of cycles. So it really slows that memory operations. So that's why we we really want to have some memory there or some kind of a hardware, so that this time could be reduced. These number of cycles, we could fetch that data quickly. Otherwise, this will be like very critical bottleneck, right? So what would happen is that between this processor and the memory, we will introduce a this cache thing, right? So we will put a cache there. Okay. So now what would happen is now this cache is now a smaller memory than this main memory. This is way smaller than this. This is not like a full-fledged kind of a memory, right? So what happens is now this cache is a faster one. It is based on uh, okay, so it is based on SRAM technology, and it really is now. So usually, approximate numbers, if we talk about the approximate numbers, so the L1 or the level 1 caches usually returns data or on approximation, because it will vary from architecture to architecture or processor to processor. But we could approximate it. For example, it will take like 4 cycles, okay, to send the data back to the processor. And even the L2 caches, uh, which are like one hierarchy below this L1 cache, or so they would also like take about 12, 15 cycles. Okay, 12, 15 cycles, and the L3s, which are usually there in multi-core processors, where L1 and L2 are shared, and L3 is like a uh, common between those multi processors or multi cores. So these would uh, take about 35 to 40 cycles, right? So now you could compare these cycles. Okay, so if data is there in this cache of level one, for example, so what would happen is it will processor will get the data in just 4 cycles, right? Instead of 200 cycles or more, even from getting the data from main memory. That's why we need those caches, and we want to have them to speed up our memory transactions, our memory operations. Okay. Whenever we want to fetch data from memory, we will definitely want that it will be present in the caches, so that we could pick that from there and save our cycles, and the uh, process remains fairly fast. Okay. So now the question comes in that, okay, so the main memory is slower, or the caches are fast and all that stuff. So we established a thing here. To, so now the question is why caches and how caches are fast, right? So if we are saying this cache is very smaller than a memory, uh, main memory, then how could it just really fasten up the things and really provide us that execution speed in terms of memory operations? How can these caches can do that, right? So let's see that how caches. So so for this we call it uh, the locality principle. Okay. So what does that mean is locality. So locality is in you could say is has two types. First one is the temporal, and second one is the spatial. Okay. So what does these mean exactly? So as we know, the caches are way smaller than the main memory. Let's assume the sizes, for example. So this is the main memory, and this is the cache. So how could this really use this locality thing? So what happens is, for example, the code we have written just a little while ago, it was like for n equals to 0, I less than 1000, let's say, and I plus plus. So we were having of some array of I, right? So what is happening here is we are fetching data from contingent memory locations, right? Continuous memory locations. Array of 0 is in is, for example, if array of 0 is here, array of 1 is the next, for example, memory location, then array of 2 is the next one, and so on, right? So it means for these types of workloads, we are fetching data from nearby locations. For example, uh, at clock cycle zero, you fetched, for example, array of 0. For example, at clock cycle 4, you are gonna get array of 1, right? Because this loop will go on and keep on calculating the results, right? So what happens is that you want to, so what is the spatial? So spatial locality comes from space, which means that when we are fetching this array of 0 from a memory location, let's say this memory location was this one, right? So this was the memory location from which we were fetching array of 0 data. Okay. So spatial locality says that because you have fetched data from this location, the next loop or the next cycle or whenever you want to like fetch data from memory, it is very highly likely that you will fetch data from near to from memory location near to this one, right? You fetched right now. So it could be like these memory locations or uh, it, so so what happens is you fetch full block rather than just fetching only this memory location for array 0. You fetch whole of the block, and this block can be defined that uh, what could be its size and what could be its size, what how it is defined, right? We will talk about it later in the session. But the principle is that instead of fetching just this single memory location, you fetch the whole block there, right? So what happens is you fetch a whole block. For example, you fetch like 16 of these memory locations, adjacent 16 locations. So you put that into this cache. Okay. So this is a spatial locality uh, that you also fetches those adjacent memory locations to the current memory fetch or memory location. Okay. So what happens is now when the loop goes on, for example, when it comes to array 1, I becomes 1, right? For I equals to 1. Now, when processor now comes into the cache, now cache will have that data inside it, right? Because we have fetched this memory location as well, right, into the cache. So cache will return that data, and instead of like these 200 cycles coming from memory to cache, we will only require 4 cycles, for example, to get that data back to the processor. Okay. And similarly, for if we have like fetched for 16 blocks or 16 of these memory locations adjacent ones, so for this loop, we will definitely be getting 6 minus 1, 15 of these data points or the data values from this cache. So now you could assume that fetching 16 of these values, we have like if we are saving, for example, 196 cycles. Let's approximate this number for the sake of understanding or visualization of this stuff. So for 15 fetches, we have saved this much of cycles actually. Otherwise, we would be going to the memory location and uh, fetching that data from here, right? From memory in 200 cycles. So we have saved this data due to the spatial locality thing. Okay. And the temporal locality is just the thing that if you use data from some certain or specific memory location. So it is, so temporal comes from time. Okay, so it means that if you used a memory location, for example, we have used, for example, array of 0, and that array of 0 has some memory location allocated for it. Okay, so we have used this, for example, in our loop 0. So now the temporal locality says, if you have used it once, okay, or this data was accessed, right, you are highly likely going to use it for using again, right? So that's why it uh, fetches this data from main memory into the cache as well. For example, if you have some kind of a loop which instead of array of I uses this one. So you have, okay, so you have a loop here from which is going from 0 to 1000, and let's say, so what happens is now that you are using this counter uh, value repeatedly, right? So because of the temporal locality, this counter's value will be in the cache, right? So what would happen is you will go to the cache and fetch that data. So now imagine fetching this counter value again and again and again from memory if it is not there in the processor, right? So this will really mess the things up and slow down the processing. Okay, so these two types of principle from spatial and temporal, we fetch the data into the memory. So okay, so there, from this discussion comes the next point actually. Okay, so we are saying that we are fetching. So let's say we have a memory. So let's assume we have a memory which has like uh, these kind of memory locations. So and then we have a cache which is smaller than a memory, right? So and it has, for example, these four, let's say four locations. So we now need to fetch data from memory, and we are saying that we do not fetch a single value because of the spatial locality, right? So spatial locality says that we are gonna fetch. Spatial locality says that we are gonna fetch a block of data rather than just the value that we required at that point, right? So what that block of memory is called, or what that block of memory is, and what is the size of that block of memory, right? So that is usually, so that is usually called the cache line. Okay. So for example, so this is the cache line. For example, if you need a 64-bit data or 32-bit data for calculating an array 0, right? But what would happen is that you will fetch a full block of data from there, not only that single value, right? So that block of data is called the cache line, or the block, you could say the cache block as well. So that line could be greater number. For example, in most of the processors, typical processors, that value is 64 bytes, for example. Okay, so 64 bytes. So 64 bytes means 64 into 8, because one byte is 8 bits. So these many bits data you fetch in a single memory transaction from main memory to our cache memory. Okay, because of the spatial locality. For example, you required only 4 bytes, 32 bit of data, but Because of that special locality, you also fetched 60 bytes of more data, which was adjacent to those 4 bytes, okay, which was contingent to those 4 bytes, and fetch that into your cache and store that into your cache so that it is available for your future transactions. Okay, so this is similar to the example we discussed before that you would, for example, if this was array 0 to array 15 kind of data example, so you have now 16 transaction covered by just using a single memory uh, transaction from here, from main memory to the cache. Okay, so now the cache would have cache line. So okay, so this is cache line. Uh, so you would say the question comes in, why 64 bytes? So it could be like different for different things. Maybe for our design, we are not using the 64 bytes. We might be using 16 bytes because it is just a training kind of a cache. Uh, but when you think of like in terms of real processors, you have to make some kind of a compromise, right? You cannot go for much larger data. For example, you cannot go for like for a typical processor or a general processor, which is you definitely would not want to go like for 512 bytes or more data, like because it will just waste the bandwidth. You will not require that much of data maybe, and then the cache is just gone, gets filled, and you have like spend a lot on the memory bandwidth side, and you would definitely not want to have like a very smaller number of bytes as well, because again, uh, the good use of special locality will not be there, fetching just two values. Uh, so, so that 64 bytes is just usually a good compromised number to have your performance increased, and uh, so from this discussion, now let's see how just the flow of cache functionality, right? Before going right into the micro arc details or that. So generally, what is the flow for a cache functionality, right? So you could say, so cache functionality, you could say. So what is that flow is? Okay. So you have a processor. Okay. So CPU. So there is your cache, and then there is the main memory. So let's say we are just talking about for L1 cache only with directly attached to the memory. So let's take this example first, without going into the L1, L2, and L3 memory hierarchies. So first, just take this example. Okay. So CPU wants to get the data from certain address. So CPU will generate that address. Okay. Um, for example, CPU says I want to get data from address 100. Okay, let's assume that address is 100. It says I want to get data from address 100. The request comes into cache. So now cache, because now CPU, when CPU generates those addresses, it generates it according to the main memory. It doesn't know that what the cache have, or it is not limited by the cache. Okay, so it generates addresses for the main memory. For example, it has like address 100, right? So now cache needs to look up. So what will cache do is it will look up this. So it has to load that. Okay, so load the data. It has to look up for this address, that whether the data for this address is present in the cache or not. Okay, so it will look up or search that address inside the cache. Okay, so and if found, okay, so what happens is it founds that address. Okay, so it knows that for address 100, the relevant data is present in the cache. Okay, and the valid data is present. So what happens is if we found, we call it, it is a cache hit. So it is a, so now this is a terminology. So it is cache hit. Okay, and it returns the data back. Uh, it returns the data back to CPU. Okay, what if it doesn't find that? So just a second to reload this. So just a second. This is reloading this. So any questions till now from you guys? So from the discussion so far. So uh, let's now look into the miss state. So what happens if this data is not found? This address is, so if this address is not found, if not found in cache, what happens? We call it cache miss. Okay, we call it cache miss. What happens when a cache misses? So there are like different types of things on that. So we will discuss that in detail. So generally, what would happen is that cache now needs to get data from memory, right? And then update itself and then get back to the CPU and all that stuff going on. So now cache goes to main memory and fetches that data. Okay. So now, my question for you guys is for optimum cache functionality or the operation in terms of improving the overall performance, what would you prefer, cache hits or cache misses? Please answer in the comments. What will you prefer? What uh, should be like Cache hits should be more or the cache misses should be more. So let's make this little interactive. So what would you prefer, cache hits or cache misses? So yes, cache hits. Yeah. So yeah, definitely you want to have cache hits more because that will reduce the number of cycles, right? You do not need to go to memory like that data. So, so we have now discussed that cache checks and search inside it to uh, check whether this is a cache, if the address is found or not, right? So now let's check into that how it do that, right? So before going into that thing, there is an important like formula that is being used in the computer architecture, and if you have gone through that computer architecture thing, you would definitely have studied this or viewed this. So this is average memory access time. Okay, yeah. So average memory access time. Okay, MAT. So how this is calculated is it is equal to hit time. So what time you take for hit, right? Plus what is your miss rate for that cache? Okay, multiplied by the miss penalty. Okay, so what is miss penalty? It is the number of cycles then you require to fetch the data from memory. So hit time is uh, so it is time taken for hit. Okay, time for hit, and miss rate is how what is the percentage of accesses actually, or the percentage of memory accesses which are the misses. Okay, and miss penalty is the number of cycles you require to fetch that data from main memory. Okay, so this really gives you the overall picture of that average memory access time. Okay, so you want to have this average memory access time as lower as possible. Okay, so that hit time is there and the miss rate is not up because we are adding that. So if like for example, if some cache that miss rate is 90%, right? So it would definitely not be a very performance friendly thing, right? And if some cache has a miss rate of like 40%, it would be like better than the 90% miss rate, right? So you have to consider this average memory access time in cycles. So you have to like reduce these kind of. So now let's look into one more important concept. So we talked about that cache checks and say that if found or not found, right? If that address found and if not found, we are saying this line, okay, right? So how does the cache checks it? Okay. So now this is one of the for me this is one of the most important topics or in the first part of this workshop because this really is the basis for, uh, for all other computations and for other design that we'll be doing. Okay, so how it checks for found or not found, right? So and we are saying that it, what does it checks? It checks the address, okay, which the CPU sends to it, right? So CPU wants to fetch data from certain memory address. So cache has that address, right? So now from that address, from this address's information, it will decide that whether it found that data inside it or not, right? Even in read or write cycles, right? So we will discuss those separately. Uh, so how would it uh, say that it found and it not found that, right? So for this, we need to look at the how the cache is being organized. Okay, so let us just see that how cache stores those addresses and what's happening inside that, right? So let's again just we are going back to our memory exam and memory visualization. So memory and the cache thing. So let's say you have a memory which has like these addresses. So let's say this is address 0, this is address 1, 2, 3, 4, 5, 6, and 7. Let's say so the memory has 8 locations. Let's assume for now. So this is the main memory, and this is your cache, which is smaller, right? So let's say it has 4 locations. Let's say, okay, which are equivalent to size of a memory locations. So it would have like memory location 1, cache location 2, 3, right? So now this memory needs to map to this cache, right? For example, if a CPU says that fetch some data from address 0, from address 0. Now the processor's request comes in, but the main memory or from which it wants to fetch that data is this one, right? So it has that data. For example, let's put 40 in it. So for example, it has 40 there, right? How now the cache will map to that, right? What happens is in case of direct mapped cache, we say that okay, let's map them. For example, just map every memory location to some certain cache location. Okay, uh, we say cache location for now. So so you have let me put this so cache so 0 is going into memory location or cache location 0. Okay, and then we say that memory location 1 data goes into the cache's location 1. Okay, so let's say that, so we are mapping. Okay, and then we say uh, that let's put the memory location three's data into cache's location 2. Okay, and then we say okay, put this memory location three's data into cache's location 3. So these 4 locations directly map to cache's locations, right? But now the memory size is bigger. It is not equivalent to the cache. Well, otherwise, the whole process really has no sense to make, right? So what happens now is that so we have now more memory locations. So we again start this. We can really start that cycle again, right? So we say, let's say that we send this data for memory location 4 again to memory so cache location 0, right? And then continue that process. So memory location 5 goes to again memory location 1, memory location 6 goes to cache's location 2, right? The blue lines, both blue lines. and then memory location 7 goes to cache's location 3. So this is now we are saying that we map the physical memory of the main memory to our cache memory, because we have those limitations of that. So now you could see that from uh, two locations, because we have total 8 locations. So exactly two locations are mapped to each location of the cache, right? So what does that mean is what does that what this flow means in terms of filling that cache. For example, now you receive the address 0, fetch the data from address 0, right? So what would happen is now this address 0 of main memory. So always keep in mind that the CPU sends the main memory's addresses, right? We have to map that main memory's address to the cache locations, right? So address 0 is there. So what would happen is, so we are saying that this address zero's data should go to memory location 0. So sorry, cache location 0, right? So it means that 40 is residing here. Okay. So now processor says, let me fetch the data from address 2. Okay. So now it checks that whether the data is in. So we will see that how it checks the data is there or not. So for now, just consider mapping. So we are talking about the mapping right now. Okay. So address equals to 2 means now it is being mapped. So this is the address 2, right? So this is the address 2. Let's say it has the data 60. Okay. So now this address 2, okay, maps to what location? The memory location 2 of the cache. So if the data is present in the cache 60, for example, it is updated, so the cache will return back that data. Otherwise, it will go to memory location 2 and fetch that data into its location 2. Okay, fetch that data into location 2, 60. Okay, and let's say then after this, memory says fetch the data from address, let's say 4. Okay, so now this data address 4, now you could see that it maps to cache location 0 again, right? So this is the example of direct mapped cache. It is direct mapping. So this memory location 4 will be directly mapped to only single location in the cache. Okay, so it is just mapped to this location. So what would happen now? So address 4 comes in. So it means the cache needs to check its location 0. So we will see that how it checks those locations and in this discussion. So let's say it checks its location 0 because address 4 is mapped to the location 0 of the map of the cache, right? So it checks for this, but it knows that it doesn't have that data from address 4. Let's say address 4 has data 100. Okay, because in this instruction or in this part, this one address 0, it has updated its location 0 with 40 from address 0, right? So it means the data for address equals to 4 is not there in the cache location 0. Cache will only check for the direct mapping. Cache will only check for this, right? For this location. So if the data is not there, it means what will happen? It is a cache miss. Okay, this is a example of cache missing. Uh, so this is a cache miss. Okay, so what would happen is now it will go to memory location 4 and again fix the data and update its value. So now instead of 60, now the data at the cache location 0 is 60, right? Oh, sorry, 100. So sorry. So the data is 100 in okay. So data is 100 at location 4. So the 100, that 100 comes in the location 0 of the cache. Okay. So this is how it will. So if again, if any instruction is there, so it says CPU again wants to have the data from address equals to 0, right? After this one, let's say. So it says fetch from address equals to 0. So it, in direct mapped cache, it is again mapping is there, right? So this address 0 is mapped to what location? To only one location in the cache. It is directly mapped, right? So when it is directly mapped, it means that it has now it will check that whether address zero's data is there. So it will definitely not have the address zero's data here because in the last instruction we have uh, put the data of address 4 there, right? 100. So what does that mean? Again, a miss, cache miss comes in, right? So this cache miss will again send the request to memory to fetch that data and update them. So now my question to all of you is kindly, so if I have an address, so let's say now this assume now this memory location goes to location 15. Okay, so it has now 15 locations, but the cache size is still 4, right? What- So what? So so what the address equals to 11 will map to the cache's location. Okay, for this cache, for this direct mapped cache. Anybody else? So, so keeping this example in mind, if the CPU sends request for address equals to 11, and we have this memory where there are 0 to 15 locations, right? So for address 11, what will be the cache location it needs to check for? Just make a quick calculation and just put that into the comments. Uh, what's the answer for this one? Right. So address equals to 11 maps to which cache location for this example? So address 11 mapped at cache 3, cache location 3. Right. So Umar has given the answer. So anybody else, you should try this one because this is a good example for just understanding of that mapping, and then we'll extract another you could say concept out of this discussion. Uh, always try to check the knowledge and be interactive with this so that we always know that what's happening there. So let's move on. So now, we now have seen the mapping thing, right? So let's get to the some of the terminologies for the caches here. Okay. Okay. So let's now dig into what. So we are saying that it checks for whether that address zero's data is there in or not. So let's find out that how the cache finds out that, right? How the cache do it, right? How the cache, how the cache finds out if the data, for a certain address is available in it, right? So let's talk about this one. This is a really important concept. So we are saying that that map cache actually has four locations, right? So, or we can say that these are the four lines, okay, cache lines that we talked a little bit uh, ago, right? Cache lines. What does this cache line mean is the block of memory data that you put into the memory transaction, right? So this is coming from memory, right? From spatial locality and all that stuff that we discussed a little while ago. So it means that these four locations are the cache lines, right? So these are the lines you could say. Line 0, line 1, line 2, and line 3, right? And we were saying that it has so each line, or when we are fetching data from memory to cache, we are saying that we are fetching a lot more of a data, right? We are not like fetching single value from that. So for instance, we said that uh, for example, we fetch 64 bytes of data, right? So what does that mean is, so let's assume we each line is of 64 bytes. Okay, so this is 64 bytes of line 0. So each line will contain 64 bytes, right? 64, 64, and then you could calculate the total size of the cache from this, right? If each line, so you have to calculate number of lines, right? So okay, right? So what will be the size of the cache? It will be like 4 into 64 bytes, right? So when we now, so when so this is for actually for fetching data from memory to cache, right? But when the CPU requests for some certain data, right? When CPU says, let's bring the data from, let's say, address 0, right? So now we have established in our last discussion that for address 0, so this is, we are talking about the direct mapped caches where each memory location, main memory's address is mapped to a single line, right? So what does that mean is address 0 will reside uh, in the line 0 of that, right? Okay. So we need to get to that line, right? So So this is so how it will find, right? So let's calculate those things and just we are going in now into some technical terms. Okay. So so this line 0 will have like 64 bytes. Okay. So let's say this type of data, 0 will have 64 bytes. So address 0, when the CPU requested, it will require, for example, if it requires 64 bits of data, it will require 8 bytes, right? It will load 8 bytes. It will not require the full 64 bytes of data, right? As you know, if it requires 32 bits, it will. So what does that mean? We need to access the bytes in each line, right? So if line 0 has 64 bytes, we need to access those uh, bytes, right? So it means we need to have those, we need to have access to those bytes as well within that line. Fetch data back, right? So now what happens is that this address is usually broken down into some fields. Okay, so the cache breaks down this address and then using those fields, it checks for availability of that address's data. Okay, so let's say if we have address 0, let's assume for now, if we have address 0, what would say it would happen is that it will check, let's say the address sizes are of 8 bits, let's say. So we have 8 bit sizes. So okay, Uh, so if we have like three bits, okay, let's if we have 8 locations, we can go for 3 bits. So we have 3 bits addresses for this example. Let's simplify that. So address 0 means it would have like 0, 0, and 0, right? So now the mapping is so uh, so for 3 bits actually we can't put that bytes into it. Let's assume we have only 2 bytes of data in line for this example, right? So let's put the data as 2 bytes. Okay. So how many bits at least you would require? Okay. So we have 2 bytes. Okay. So we are gonna select from these 2 bytes. So each line for this example is of 2 bytes. Okay. 8 bits of data is there. 8 bits of data is here. So let's say so from for selecting a byte from this, we will require a single bit, right? We say that okay, we need a single bit to uh, check for this, right? And then out of these 2 lines, sorry, 4 lines, we need to select one line, right? So the other 2 bits would be there for selecting those lines, right? Because 4 options. So we are saying that for line 0, there would be like 0, 0. For line 1, it will be 0, 1. For line 2, it will be 1, 0. And for line 3, it will be 1, 1, right? So what does that mean is, so these next 2 bits will tell the cache to look into which line, right? And then it will require some of bits actually here. If there are, you could say, larger number of memories, so memory addresses. So for example, we put a two bit number here, right? We put a 2-bit number here. Okay. So how would this map actually? So let's put our memory addresses right now. So 0. So let's say 0, 0, 0, right? Let's put in 3 bits and then we'll see. Then we will have memory address as 0, 0, 1. Then we will have address as, so we are now thinking as a cache. Okay. So we are trying to figure out that how would cache really finds what data is present in the cache and what is not, right? So let's say memory. So these are the memory locations. We were saying that in our example there are 8 memory locations. So 0, 1, 1, 100 101, and let's say it is so 110 and 111. Okay, so let's find some patterns. Okay, um, for this direct mapped kind of a cache. So let us find the patterns. Please follow along those patterns. We will be like discussing this as our examples so that we build this along. So for example, these are the four lines and these are the memory locations, right? So what we are saying here is we are putting a single memory location. For example, if it say what whatever the size is, it into a single line, right? So what you are observing is just consider these two bits. Okay, consider these two bits. So if this is like 00, what does that mean is? So it means it is indicating to some pattern, right? So this is 01, this is 10, this is the simplest form of kind of example. So we will dive from this. We will continue some complexer ones as well. So what you are finding here is, so these two bits are 00, these are 01, this is 10 and 11. And again, from 4 onwards, this is going like this, right? 1011. So if you look closely to this direct mapping kind of a thing, you would see that 00 maps. So this address maps to line 0, right? This maps to line 1. This maps to line 2, as we discussed before. Line 3, line 4, uh, sorry, line 1. So this is line 0 again because we have lines, 4 lines. So this is 10. This is line 2. This is line again 3, right? So we discussed this before in visual representation, but now we are seeing it in the form of addresses, right? So for this example, if I take the first two bits of the addresses, let's say the addresses are of 3 bits, right? Let's say for now. So what it is indicating? Cache will look into the first 2 bits and say, and it will understand that what line it should access, right? So for example, if the first 2 bits are 00, it will access line 0, right? It will check for line 0. It will reach out to line 0. So this is the first step. Okay. So this you call as the index bits, right? Index bits. What is the index of your line actually? Okay. So we will look into much better version of this one in the coming session. So let's build it from like very simpler concept. So if anybody is like lagging behind, so it will definitely be with the pace of it. So now from, so if I say now, for example, if I just give you a much larger number, let's say we have now this as a, so this is address, right? So let's assume we have now a much bigger kind of a memory, but the cache size is the same. It has 4 lines, and if each line just corresponds to a single memory location size, right? So let's say this is the address. So now, can anybody of you tell what will be the line cache needs to access? Check. Okay. So what line it will access just from this address for this example. So what would be the line number that cache will check for? Anybody else? So for 4-line cache, we have discussed that the first two LSB bits will be the index bits. Means they will be used to access some certain line or some certain index one, right? So what is the line number for this cache, for our example, right? For this address, which I have written here, is comment in the comment section so that we could really move on with flow. Anybody else? This is very simple kind of an answer. You have to just look for first two bits, right? Just for the first two bits for this cache, for this example. We will put that into much formal thing later in the session, but for now, so you have to look for this first two bits, right? So this whole map, so this whole address will map to first two bits, to line two, right? Line number two. So now, as the cache uh, has determined which line to check for the data, it now a single bit has left, right? So you are seeing this bit, right? So out of these three bits, yeah, so the line two is there. So now there is a single bit left, right? In our three bit of. So now you could see that memory address 0 and the memory address 4, right? So this is the memory address 0, this is memory address 4. They both are mapping to line 0, right? But what now determines is what for what you could say address data is present in the memory location. You now need to check that last bit, right? How are you gonna check this last bit for this? So these bits are known as the tag bits. Okay, so these are the tag bits, right? So what these tag bits now determine is, so for instance, yeah, now you need you so the cache determined that it needs to access data from line 0. It will check for this for these tags. If the tag 0 is present in line 0, it means the data for address 0 is present there for from memory location. If the tag is equals to 1 there in the line 0, what does that mean is the data for address 4 is present in the cache. Okay. So it means now from hardware perspective, how the caches are doing this. So for checking the line or the index, it has to compare, right? So let's assume, so we have these four lines. What would happen is cache would check for lines. So it means it would have comparator, right? It would have like comparator to check for whether it is line 0, it is line 1, it is line 2 or line 3, right? So let's line 0, or it is line 1, it is line 2, and then line 3. So then each line actually or each index of the cache will contain some data, right? So what does the data means is it will have some certain arrays inside it for checking what kind of message it has, right? So what would these be? So each line would have, let's start from the simpler one and then we'll go on forward. So each line will have like the data. So it will have data, it will have tags stored in it. And if we are saying that 0 or 1 are present, right? So what if they are present? For example, 0 is present in the tags memory as by default, right? We haven't we haven't fetched anything from main memory, right? By default, there is a tag 0 present there. So what would that mean is it will check for line 0, and when it goes to the tags section, it will say that tag 0 is there. So it will say, okay, I have found the data for address 0, but that would be not the right data because there was no data that being fetched from main memory. Here is always, you could say, a valid bit as well with each line, right? With each location, you could say, for direct map cache. Okay, so this line will consist of these three types of data. It will have data, which is data, right? It will have tag, it will have valid. So now let's simulate this map, that how does it work along with the main memory. How the tag bits will work and how the valid bit will work and how those lines will work. So again, just taking our example of main memory of eight memory locations, let's say, simpler example. So this is this. We to check for these. Okay. So so let's put this. So assume this is the memory location 0. This is 1. This is very simplified example. So just for understanding and visualization, don't just put that into a real. So we will do that later in the session. So 6, 7. For example, these are 8 memory locations for this example, and the same cache, which is of 8 bits, with 4 lines actually. So let's say this is the cache uh, with 4 lines, right? So this is line 0, this is line 1, this is line 2, this is line 3. So now each line will contain 3 kind of arrays for now, right? Which will be the data, tags, and the valid bit. Okay. So it will have like data, tags, and valid in there. So there will be, this is the data, this is the tags. It will store the tags inside it, right? So the cache will store this information and the valid bit, and it will be true for all of the lines. Okay. So now let's first define our memory addresses. Okay, so we have a program. So let's say we want to simulate the data. Uh, so let's say we have uh, a program which is accessing memory addresses in this. pattern, right? So let's put that in. So let's put that in. So for example, in first cycle, it accesses address 3. In the second cycle, it address which it accesses is 5. And let's say it is sending for load. Okay, it is sending for so it is sending the data. So for example, at address 5, it is again loading that data. Then from in third, from address 7, then in fourth one, it is from address 8, loading data, right? So first just take the examples of loads, and then we'll simulate towards the stores as well. So let's say we have these addresses, right? So 8, 3, 5, 7, 8, and then we repeat those. So let's say this is 8, then we will go for fifth cycle with 4, then 6. Okay, so 3, 5, 7, 8, 4, 6. So we are going to simulate these loads. Let's say in the main memory, and this is the cache. So let's say we in the main memory at the starting point, we have these data. Okay, so 20, 30, 40, 50, 60, 70, and 80. Okay, so let's assume that. So what happens now is that so now what happens is that we so let's assume so first address is 3, right? So it means this 3. So let's first find out that for to which line it will really uh, really goes to, right? So 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 for 3 it is like 0, 1, 1, right? It means it will go to L3 or the line 3, right? So for from this so the first one is a miss, right? So this is a miss. So this misses the cache because in the start all the valids will be 0, right? Because there is no valid data there right now. Okay, so all the valids will be 0. So first transaction when we are looking for address 3, it goes into the line 3 from these two bits we saw, and it will go to the line 3, and from this line 3 we found that the data is not valid there. So whenever the data is not valid and the valid bit is 0, there is no point in checking the tags or data or something else, right? Because there is no valid data right now. What would happen is then can send request to memory and we load the data 40 here. Okay, so we load the data 40. Oh, sorry, this is not the data point. This is the tag one. So this is the tag. So we need so when the data is being fetched from this location 3, this becomes 40 here in line 3, and the tag becomes, so we have said that the tag is this third bit, right? So for 3, the tags comes in here as 0. Okay, and now this valid, because now the valid data has arrived, right? We have now a valid data here. So see, we will make this bit valid as the 1. So the tag will save this information for itself, right? So now the data from main memory 40, which was 14 in the address 3, came in cache, and now cache provides it to the processor and all the processing happens, whatever. So let's say for address 5, now another loads comes in and CPU requests memory to send the data back. So now what will happen is, again, we need to check the which line it is in, right? So 5 is 1, 0, and 1, right? So 1, 0 means line number, line number. So the line number is now 0. So the line number is 0, 1. 0 is line number 1. Okay. So the line number is 0, 1. So line 1. So we're talking about line 1. So again, in line 1, there is no valid bit, right? It means there is no valid bit there. Again, cache has to send the request to main memory to fetch that data from memory location 5, where the data is 60, right? So what happens is now, again, at line 1, we will write the 60, and now the tag is 1, right? The tag is 1. So now cache stored the tag 1, data 60, and uh, this is now being changed to valid data, right? This field. So now all this information is being stored by the cache in the second transaction. So again, this is also miss, right? This is a miss. So now for address 7, we again need to calculate uh, what is the line number and what is the tag, right? We have to extract. Okay, so is the voice clear now, or is it still cutting, or is it clear? Also, okay, so for address 7, we have like 111. What does that mean is 11 means 3. So line 3, we have to access the line 3. So there is now interesting thing. So line 3 has now the valid data, right? So now it needs to compare the tags. So the tag which is stored in the cache location is 0, and for the tag for this address is 1, right? So 0 is not equal to 1. It means it now needs to update this value. It needs to update this data, right? Because this doesn't match to the address, right? So now it will what it will happen is again there is a miss. What again? So this is a miss again, and we will fetch the data from memory 7, which is like 80, right? So though the data is valid still, okay. So though the data is valid, but now the tags are not matching. So this is a miss, right? Because it means that for that particular address, there is no data there, right? Okay. So now this tag will be updated with 1. Okay. So this data here, so we will update this with 1. So the cache will update 1. Okay. So now this is 1. And for this one, now that this data also we get updated. So this is 80. So we will make this, right? So this is now 80 here. So this is okay. And the second comparison is for the tags. Okay. So if the data is valid and the tag matches, then there is a hit, right? And the first one is obviously when it looks up or it searches for the lines. So which line number it should go. Okay. So any questions till now? If you have any questions during this session, please put that into the comment section so that we answer that. I do not have any questions or confusions about what's happening there. So from now on, so you are seeing this now. There is a one issue in this example or in this version of things. It is because we have a line which is very small, right? Here you could see this line 0 which we are saying that this is line 0. It is very uh, smaller kind of a line, right? Because it doesn't have much data in it, right? uh, it contains only the data of that particular address, right? So this is a direct mapping. It needs to evict the other data, right? For example, if 3 we were loading 3, uh, if 3 was not there, we were just evicting it and putting that in. But now let's say we for this we were fetching data only for this memory location, right? So we were saying that the data that is coming into the cache from the memory is for only a single memory location, right? For this example till now, right? For example, when we filled this data with memory location 3, we said that okay, from memory location 3, this data will arrive here, okay? So this was not true for the caches. So we have talked about this before. So due to this, you are seeing a lot of misses. So for all of these 1, 2, 3, 4, 5 locations, 3, 5, 7, 4, 8, 6, you will see that these all will miss according to this example. If we have this line, so here the line is just, for example, this cache line or the block of memory that we are fetching from main memory is just equal to that memory location's address, right? Or data, right? For example, we were only fetching 40. We only fetched 60 from address 5. So this is true for temporal locality, but this is not the spatial locality. This violates the spatial locality. So if we put the spatial locality into this, right, into this example, you will see that there will be lot more of hits coming in. even for this example. Okay. So now uh, we will increase our cache line. So it will now fetch four memory locations in each transaction. Okay. So for this example, with fetching a single memory location from memory to cache, it, all these memory addresses would miss. Okay. But now when we just put that into a special locality principle. Okay. What does that mean is, so let's deep dive now into that. So the cache is same. So cache is not like we are not changing the cache. So let's say now, but we have now increased this cache line, right? So the data coming from the memory is now greater. For example, if there were 32 bits of data before, we were just fetching 4 bytes of data, right? So now we are saying that we are not going to be fetching 4 bytes, we will be fetching 16 bytes of data from memory. So what does that mean is, if the request comes for load address 3, so the data that will be fetched from main memory would be for uh, address 3, from address 4, from address 5, and address 6. Okay. So we will fetch the data from now 4 memory locations, because what we are saying is, now though we required the address 3, but we also have a special locality, which is the principle for the cache, and that's why the caches exist and are useful. Uh, is that we will now fetch that 4 memory locations into our cache. Okay. So what would happen? So when the data comes from memory location 3, it will go to like to the line 3, right? It fills the line 3 or block 3 of the cache, right? Where it is. Okay, so let's just erase it a bit. So I am just erasing. Okay, just skip that 8, right? So just you could have like 15 locations, so that in that case you could do that. But let's stick to the 7. So just skip the 8, right? So let's in the start we have all bits 0, right? Again, simulating the example with special locality. So these are all zeros in the start. So the address 3 loads in 011, so it loads the data into L3. 40 comes in with tag number 0, right? But now we are saying that we are using special locality. So instead of uh, only a single value, we are fetching 4 uh, blocks of data from there. So this will be like 16 bytes of data being fetched from memory. So it will update the 4 address 4 as well. So for 4, we have 1, 0, and 0, right? That means it will go into line 0 and with tag 1. So here line 0 is this. So tag 1 comes in. So data in 4 is 50. So the 50 comes in, and this valid bit setting. Okay, so now this is valid data, because this data has arrived from memory, and this is a valid copy of the data that is present in the location 4 in the main memory, right? Again, for 5, we will be going into the line 1, right? From this 01 is the line 1, and for this one is the tag, right? For our example, so tag will come 1, line 1, and the data is in location 5 that we fetched from the main memory is 60, right? So it comes in as 60, and the valid bit sets in. So the valid bit is set. So we set the valid bit. And for 6, we have 1 1 0, so that we are filling the line 2 for the cache, and this is tag is 1, and the data in 6 is 70, so we fetch the data 70. So now, uh, and let's make it 1 as well. So these both valid bits 1, right? So let's make them 1 and 1. So now, even in the first cycle, when we uh, fetched only data for the address 3, because we fetched more data, right, from memory, and we bought the 16 bytes instead of 4 bytes, what happens is now we have data here in residing in the cache for address 3, 4, 5, and 6, right? So now when we now load this or execute the same program, what would we see? We would see is when we load it from address 5, so it goes into L1 where it finds the tag 1 because the tag is 1, the valid is 1. It means it gets hit here. So this was miss and this got hit, right? It gets the memory hit part because we found the data from for address 5 inside the memory or inside the cache. Okay. So this got hit. So address 7 will definitely miss. Uh, so when the address 7 misses, right? So this cache will again gets updated, right? So how would this really gets updated? You have to again go through the specialty thing. So now it might fetch, for example, 0, 1, 2, and 7, right? For example, it might fetch 0, 1, 2, and 7. So it means this data gets updated. Okay, this will be miss. So so just skip this one, and this is just a mini kind of an assignment for you guys for now, that you need to find whether uh, after loading 7, right? So while loading 7, you have to load like 0, 1, 2, 3 as well. For 4 and 6, what will it be, right? Will it be a hit or miss for 4 and 6? So this is quite a straightforward kind of thing. So, uh, so 7 misses because 7th data is not there. Let's check how, right? So for example, 7 is 1 1 1. So line number is 3, right? So we will check into L3, but the tag is 1, right? So the address 7's tag is 1, but the tag that is stored inside the cache is 0. So there is the tag mismatch. Uh, though the data was valid, but it was valid for address 3, not for 7. Okay, so that's why it misses, right? So it misses it, and can anybody answer that if we load the data for 7 and its adjacent memory locations, which are, for example, 0, 1, 2, 3. Okay, so 0, 1, 2, and 7. So these 16 bytes will be loaded. So 4 will be hit or miss. 4 will be hit. No, I guess 4 will not be hit. So we are not going upwards. Okay, so let's assume we are fetching. If we are going with 7, we are getting 0, 1, and 2 along with 7. Okay. So these four locations have been taken into this memory, into this cache. Okay. So what would happen is that instead of 4, we will have like 0 there. So L0 will get updated. Okay. Um, because 0 means 0 0, so it will go into the line 0. And because the tag is 0 for 0, tag will be 0. and the data will be for the address number 0. So the address 0 is 10, so we'll get 10 in the address 0. So when we got for the 7, right? So for 4, when we set the 4, right? So 4 is 100, we will go into line 0, but there is a tag mismatch because it was updated for address 0 before when we fetch the 7. So it's 1 and 0 gets mismatched, and we got a miss for 4. Okay, so what about the 6? Anybody else? So my question was, what will happen for 4 and 6 if the 7 misses it, right? Will it be a hit or miss? Will the 6 be a hit or a miss? Can it be answered? So 4 will be a miss, and 6, you can answer it. Then we are fetching 16 bytes of data. Anybody can try this one? Six also hit. Yes, this is true. Because when we missed the 4, so the data that will be fetched will be for address number 4. That will be for address 4. That will be for address 5 and 6, 7, right? 4, 5, 6, 7. So we will fetch the 4 memory locations data into our cache, right? So when we got the address 6, we will definitely find that inside our cache, and it gets it. Now you could see that out of these, like 5 misses, because in the previous example when we were not fetching larger block of data from memory, they were all missing, right? They were going to only hit in case of then exactly that. So okay, so but in this case, when we are fetching like 4 memory locations or more blocks of data from memory, we are hitting more, right? We have hit for uh, like 2 3 times, right? Okay, so this is the benefit of the spatial and the temporal equality, and this is how the cache, in the case of direct map, actually this is rough one. We'll structure more into a form, right? So this is how the cache functionality will flow, how it will compare those uh, data, right? So there is a question which, if I understand it right, is that when you load the data for first time, the same cache line, it always hit, but very always miss. So it will depend that if that cache line is, if the data is in the cache, right? When you are fetching, exactly for the first time, right? Uh, you could say that after the reset type. So this is always gonna miss, right? So there are different types of misses as well. So this miss or hit will always depend on what data is present, right? Inside the cache. For example, if we are fetching 8 bytes of data instead of 16 bytes, this miss hit ratio can definitely change, right? If we have a larger cache here, let's assume we have a cache with 8 lines uh, for this example, and main memory with, for example, 16 lines, and then we map that into a different locations, and we are fetching more data, for example, 8 memory blocks per transaction. So this will definitely depend upon which data is there inside your cache, right? So you need to check with the tags and the line thing. So index bits, using the index bits, and okay. So now, if there are no questions, let's move forward a bit. So let's now put this a raw example into a much structured form, into much like polished form. And okay, so for this example, what was happening, right? So let's do some uh, formal things here. So what was happening in this example? Let me just erase a bit of this. So let's clarify some things and now build on this thing. One thing that you might have noticed if you are like going into this. So when we were fetching like 16 bytes of data, we were saying that this is a single cache line, right? Okay, we were saying that this is a single cache line. But here in this example of this cache, we are saying that line 0, line 1, line 2, line 3, right? So this is exactly, this is not actually right for this example, because when we say that we have fetched the cache line, right? So that cache line is now the one parameter, right? Okay. So we say, so instead of saying this line 0, right? So let's say, so this is a complete line, right? This was a complete line, because what does it mean is that we were fetching, for example, this data, right, from memory. So we were saying it, this is a cache line. So what we were fetching is, so what is a line is? Line is the block of memory that you fetch in a single transaction from memory to the cache. Okay. So we are fetching these 4 blocks of data, right? We are fetching this 4 blocks, 3, 4, 5, 6, for example. So these 4 blocks actually form a single line. not the L, so not these horizontal ones. So if I could put this as, okay, so now, so this is a single line data, right? This is a single line, right? Right? Okay. So what does that mean is that single line. So now we are gonna see this data as the line. So when we say that this line starts from zero, let's assume this line starts from zero. So you have address zero. Okay. So you have address zero. Okay. So you are now gonna fetch this data from address zero. Okay. What would happen is you would fetch address zero, address one, address 2, and address 3, because we are saying this each memory location is of 4 bytes, and we are fetching the cache line as 16 bytes of data, right? What does that mean is that in, so this whole is now a line 0. This is a line 0. Okay. Now, just to clarify more, okay, so this is a line 0. Okay. And then, for example, if we have uh, another line that comes in, or so within this line, you need to find the, for example, if you need to fetch this data, right, for one, memory address one, then you fetch it using the byte offsets, for example. Okay. So for example, for this, you would not definitely need those index bits, right? Because there is only a single line in this set, right? There was no, okay. Or if we could visualize this in a row, let me put that into a row, okay, uh, instead of this vertical thing, so it will be more visible to you guys. So let us put this into a row. So now consider this a bigger cache with, for example, 3 lines, right? Okay, so it has now 3 lines. Now these lines are not same which we were talking before. So these lines now directly map the data that you are fetching, right? For example, if you are fetching data from 0 to 3, this line is now starting from 0 till 3, right? So it has now 16 bytes of data. This has 16 bytes of data. Okay, this L0. From, for example, in this case, it would have from, so again, each block would have definitely their valid tags, valid tag, and data bits. Okay, again, this will be divided into valid tag and data bits. But now it will, in whole, it contains 16 bytes of data, right? Coming from these locations. And again, L1, L2, and L3. So now whole of the memory block that you fetch reside in a single line, right? That you call as a single line, right? So now, in order to, you could say, fetch data from here, or access those data, because we are saying that now there are 4 memory locations here, one, two, three, four, right? Because in a single memory transaction, we are fetching 4 memory locations, 0, 1, 2, 3, for example. So what if I need to fetch data from address one, right? Let's discuss that scenario. before going into the other uh, terminologies. So there will be a difference of some terminologies here. We 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 said that index or that stuff. So, okay. So let's so for direct mapped cache. So this is for the direct map cache exactly. So in order to access these, uh, we have to consider what is the addressability of your cache. So this is a new term. Uh, Let us put this. This is the addressability of the cache. Okay. So what is the addressability? What does addressability means? It means that what number of minimum data bits can you access from inside a cache, right? For example, in most cases we usually go for byte addressable memories, right? So you could access single byte level of data, right? For example, if I there are 16 bytes, you could access those 16 bytes. You could exactly. But for our example, if we are putting these, for example, we are putting these memory addresses as 0, 1, 2, 3, and we are saying that it contains 4 bytes. What does that mean? Is this memory is word addressable, means the data lesser than 4 bytes you cannot access them like very uh, with the memory address, with a unique memory address, right? Because if I provide the memory address 1, it means I will be getting 32 bits data from this memory address. If I put 2, I will be pointing out to another 32 bit of data, right? But this is not typically the case in industry level where we usually use byte addressable memories, right? So what does that mean is for byte addressability, though there is a 32 bit of data here, but is all 4 bytes, 8 bytes, 4 bytes will have their unique addresses. This is, for example, this is 0. If it has 4 bytes, right? So let's say it has 4 bytes. What would happen is this will be 0, this will be 1, this will be 2, and this will be 3. Okay, so these bytes have unique addresses, and the next address, this is known as the base address. Okay, so this is the base. It will start from 4. So 4 will, so there will be increment of 4 in each memory location if we are saying that it is each of 32 bits, right? Because this is a byte addressable memory, assigning each unique address to a single byte rather than a word. So if we have a word addressable memory, it means we will be assigning 0 to whole of these 32 bits, and the next memory base address will start from 1. Okay. So first we have to, you could say, determine this addressability. For example, for our example, let's take this as a word addressable. Okay, let's take it as a word addressable. So what would happen is word addressability means now with each memory address you could access minimum of a 32 bits of data. Okay, because there's no unique addresses for data less than 32 bits. Okay, uh, so let's see now how this addressability now will help us in finding these locations for a particular data, right? So we are saying that 16 bytes of data has come in, right, in a single cache line. So this is another single cache line, this row, right? This is a line, another line, and this is third line, and the fourth line, and so on, right? So address 0 sends of 16 bytes of data. So we are saying that we are accessing 4 bytes or words, right? Addressabilities. So it means then we need to address 4 words, right? because there will be total four words in this line, right? Word mean a 32 bit of data, right? So line 0 will contain four words. So this will be, for example, word 0, this will be word 1, this will be word 2, and this will be word 3. So these all four words are coming from application 0, 1, 2, 3, right? Because we have fetched this line. For example, right? We are fetching four words inside the L0. So this is known as the offset. Okay. So for accessing, for example, now CPU wants to access the address 1, wants to get up from address 1. So address 1 is here, right? It is in line 0, it is in line 0 at location number 1 for that word. Okay. This is how this is offset, right? This is called as the offset. Okay. So this is the offset. What does the offset means? It is the location of the particular addressable data. For example, it was if it was byte addressable, then each byte would have these unique memory addresses, right? For example, 16 bytes would have like 0 to 15 written in this line 0. Okay. So now you are talking in terms of line, cache line, cache line, cache line, cache line. Okay. So this cache line, which is the block of data coming from the main memory. We are saying we are getting 16 bytes of data, and we are saying that this memory is 4 byte addressable or word addressable, which means those 16 bytes would be addressed like 0, 1, 2, 3. This addressability within that line is known as the offset. Okay, so this is the line. Oh, okay. So anybody else also facing the voice issue? Let me know if some other one is also facing the issue. Okay, let's now. So this is the offset. So let's take more complexer examples to now calculate the offset. And second thing is now uh, is the number of lines do you have? For example, let's take this example that we have 4 lines. So now this cache has 4 lines: L0, L1, L2, L3. Okay. So, so what would be the size of this line is? So, sorry, for the size of this cache is. So this is very really simple. So each cache line is of 16 bytes. So we multiply it with the number of lines we have. So we have like uh, 4 lines. So multiplied 4, or if you want to get it in bits, you could multiply it with 8. You would get the number in bits. So, so now you have 4 lines actually in this cache. Let's assume now our memory is bigger, so we could like have as much memory locations as well. So don't limit that memory now. So what would happen now is we would need bits to access these lines as well. Okay, so if there are 4 lines, what does that mean? We would require 2 to access all of these 4 lines, right? So these two bits which are required to access these lines are known as, or we call it as, the index bits. Okay, so the concept is same that we talked about earlier, but difference was that in that example that we discussed a little bit earlier, that the cache line was just of 4 bytes, and and the data was missing and cache was missing, and we were not like performing very good on that because there was no special locality in that cache, right? But for now, as the special locality is there, so the cache line is now larger with 16 bits of data, 16 bytes of data, and there are more lines like L0, L1, L2, 3. So those line has to be accessed using some bits, right? So it means that we need 2 bits of index, 4 bits of offset, 2 bits of index, and the remaining bits will be uh, left for the tag. Let's assume, let's assume we have now the memory addresses uh, of size 16. Let's say, okay. So now the memory addresses are of 16 bits. Okay, so memory addresses of 16 bits. So what happen is, so we will require 2 bits of index. So the usually what happens is that the first 4 bits are for the offsets. Okay, so first 4 bits from LSC sides is the offset, and then the next 2 bits are for indexing this cache, for finding the line number, right? And the remaining 10 bits will be the tag. So this 10 bits. So this is offset, this is index, and this is the tag. Okay, this is how you could calculate the offsets, the index, and the tags for a cache. So if we summarize this concept into more structured form, what will be what kind of information we will need to calculate these tags, index, or offsets, right? First information will be the cache line. Okay, so what is the size of your cache line? So what will be the size of the cache line? So you need to have that information, or for this calculation of tags or for direct map. So cache line. mm, So what would be the information required? It will be the cache line, and then you will require the information is number of lines a cache has, right? And your addressability for the memory, and then what is the uh, memory address size, right? So let's take a quick example, mathematical one, and then we'll deep dive into our coding session. We will start after this example. We will also have a question after this mathematical calculation of tags or bits and everything, so that everything is cleared up. So let's say we have a cache line. Okay, so we have a We have a cache line of 64 bytes. So number of lines this cache has is 16. So addressability is 8 bytes. Sorry, uh, byte addressable. Okay, byte addressable. So let me just change the color of these. So we have cache line of 64 bytes. Uh, Number of cache lines cache has is 16, and this is the byte addressable. And address size for memory address size that we are sending is 32 bits. Okay. And one more concept out of this, we will discuss that in when we discuss the set associative caches in the second half. But now for the direct math caches, we are staying to this terminology that the things are more clear. So now let's calculate our number of bits required for offset, number of bits required for tags, and then the remaining bits will be the number of tags bits, right? Okay, so let's just do it. So let us calculate this example here. Okay, so for offset, we say that we need to have addressability and the cache line size. Okay, so we have 64 bytes, and we are saying that we are addressing them as bytes. Okay, so it means those 64 bytes will have their own unique addresses, right? So we need to access for offset, we need to access 64 bytes, right? For accessing 64 bytes, we will need how many bits? We need 6 bits, right? Okay. And for indexes, right? For indexes, how many lines this cache has is 16. It means so addressing those 16 lines, or to assign a unique address or unique ID to those 16 lines will require 4 bits, right? Uh, so we will be using 4 bits for indexing our lines in the cache, inside that cache, right? And the third thing is tags. So what is tag bits left? So this will be like uh, what was the address width or the address size minus the bits allocated for index bits plus offset bits, right? So this will be equal to 32 minus the index bits were 4, and we have offset bits is 6, right? So this will be 32 minus 10. So 22 bits will be there for tags. Okay. So using the 32-bit address sizes, you could have a physical memory or the main memory of the size equal to 2 raised to power 32, right? Because you have now 2 raised to power 32 addresses. Okay. So this is how you could calculate those tags, next offsets, and then the cache will compare those inside it and place those data coming from memory in the form of lines. And yes, and then you could address those access those addresses. So my question to you guys for solving this is, let's assume we now have a bits of 16 bits of address size. Cache line is 64 bytes. Um, so we do not have the data for the number of lines for now. We have the cache size. Okay, we have the cache size, which is equal to 2048 bytes. Okay, cache size is 2048 bytes. Okay, so cache size is full cache size, means the memory size for a cache is 2048 bytes. Cache line is 64 bytes. Addressability is, let's say it is byte addressable. Let's not change that. And the address size for the you could say for memory addresses is 16 bits. Calculate the number of bits required for offset, index, and tags bits. Put that into the comments and find the answer for this one. This will be like quite interesting. Let's just session up our concepts before going into the coding part. So we'll be right after this assignment, we will like put like 2, 3, 4 minutes on this assignment. Use your time and calculate this example. And this is for the direct mapped cache. So this is for direct mapped cache. We are discussing only the direct map right now, not going into the associativity. Okay. So let's take your few minutes, 2, 3, 4 minutes to calculate this and put your results in the comment section. Then we will move to the our design design part of the hardware for direct mapped cache. Let's try. Everybody just try this out. But, if any confusion or the question arises, it could be solved right now, right? So just calculate the offset, index bits, and the tags for this example. So if any question or confusion comes in, do you mind please clarify it right now so that it doesn't carry into the design part as well? Okay. So offset bits 6 and text bits 5, tag bits 5. So what is the calculation for index bits 5? How many lines are there in this cache? Um, Everybody just try to put that assignment or try to answer this question. Because if any question or confusion comes in, we can definitely sort it out there before going into our coding session, which is just starting in a couple of minutes. Yeah, right. So this is the correct approach. So you could just divide the total cache size by the cache line, so you will get the number of lines inside a cache. So this is the right thing. Uh, so this is the right answer. Actually, so anybody has also answer, you could definitely put that into the comments, and we could look into that. If you have any questions, you can put that also in the comments. Uh, so now let's move towards the coding session. So let's put that to share that screen and so let me know when you are like seeing the coding part of coding screen, the 3D playground one. So we are now starting on the coding part right now. Okay, now before just diving into the coding part, so this memory model one, we are using just a memory model that interacts with the cache, right? So this model gives back the result in you could say in 4 cycles. So okay, so this is the model for interacting with the cache. So whenever the cache requests to the memory, this model gives back the result in 4 cycles, uh, and it has its own interface and lots. So this file will be provided to those who have registered for it, the paid structure. So these coding assignments will be provided to them. So let's discuss the microarchitecture before going into the coding stuff. So let's discuss some of the things here. So first, let us discuss the high level kind of diagram for this, or block diagram. So let me just draw that. Okay. So what kind of thing this of? So we would be having this direct mapped cache here. So this is a direct map cache block diagram. Let's just take a bigger picture of before going the direct map cache. So it will contain different sub module kind of things or some functionalities in terms of doing stuff. So what would it have is it would have like tag arrays to store the tags for each of the addresses in each line. It will have data arrays containing the data of particular address, then the valid arrays along them, which we discussed in a little while ago as well. And then it will have a hit comparator, uh, whether it is a hit or a miss case, right? And then if it is a miss, it requires to have a fill FSM. So it will have a fill FSM, which means so it will be getting request from CPU, right? So this is getting request from CPU, which will definitely contain the address coming from CPU, read or write, whether it is a read or write operation, it wants to load or store, right? And in the case of writing back to the cache, it will send the write data as well, right? And then it will definitely go to memory in case of, and we are using a memory model in place of this memory, right? And the CPU is being like done to test bench where we are sending the request to the cache, this direct map cache. Uh, okay, so some of the parameters of this cache that I wanted to discuss quickly. So this cache is a direct map cache. Data width or the address width is 32 bits. Okay, so address is 32 bits. Data width is 32 bits. Cache size is, so this is parameterizable a bit. So don't be like so this is 4 KB of cache size, and the line size is 64 bytes. Okay, so this is, so if you just divide this now with the example that we resolved a little while ago. So cache size 4 KB, size is like 64 bytes. So the number of lines would be, you could calculate from here, which would be like 64. Uh, so from these computations, the offset actually, so we will be using a couple of, you could say, offsets. First one will be the byte offset. Okay. Then we will be using word offset. Okay. And then we will be using index, and then the remaining bits will remain for tag. So byte offset means number of bytes. So there will be 4 bytes in a word. So it means that the first 2 bits will be reserved for bytes. Then for word offset, we will be, because there are total 16 words. per line because there are 64 bytes, right? So there will be 16 words. So for 16 words, we will be using 5 down to 2 in 4 bits for that. And for indexing, because this is again 64 bytes of data, so indexing these 64, sorry, 64 number of lines are 64, dividing the cache size and the line size. So index will be 6 bits, that will be from 11 down to 6, and the remaining bits will be for tag comparison, and it will be stored in the tag. So it is like 20 bits of tag, 6 bits of index, 4 bits for word offsets, and 2 bits for byte offset within that word. Okay. So these are some of the parameters for this cache that we will be using. Uh, so one of the simplification that we have done there is that it will send the CPU read or write. Okay. So CPU read and CPU write, for example. So they cannot be simultaneously one. So we are assuming this uh, in building the simplified form of a direct map cache. So that then there will be like memory address going to the memory and getting the result back. Uh, so so now discussing these valid bits or tags. So let's take a look at them as well. So these valid bits will be, so valids will be per line for now. Okay. So one valid bit per line. Uh, okay. And the tag array, uh, again, for each cache line, there will be tag arrays uh, containing the tags for that particular line. Okay. So the tags array will be there. And then definitely there will be data array per line containing 16 words per line. Okay. So let's now just look quickly into the mishandling or the miss FSM as well before just going into the code thing. So in case of miss, cache miss, it needs to go to the memory, right? So for that, we have to track what kind of state the cache is in. So we have idle state for that. So idle means cache is operating normally, means there's hit cases and the stuff are going on. And then if uh, miss cache misses, so we have to go to mem request or mem req uh, state in which we issue a memory request to memory chip, issue memory request. So to read data from memory. Okay. So this is the first one. This is the second one. Then we have to wait for the memory, right? For example, in our case, this wait is for 4 cycles. So we have to wait for response from memory in this from memory. And the fourth will be the fill. So this, what is this? We receive the data. Now we are putting that data into, writing this data into the our line, cache line, right? Data into cache. Okay. and the fifth one will be respond, which is now sending the data back to CPU. Okay, sending the data back to CPU. So these five FSM states uh, will be there. Okay, so for the write policies, we are using the write through policy and write allocate policy. Okay, what are these policies? We will discuss in the second hour of our session. Okay, so just for now, you could just skip that part. So, so for from the timing point of view, so timing point of view, it will be like one cycle for cache hit or for cache hit. Okay, data will be returned in one cycle cache hit, whether it is read or write. In case of miss, it will be like a larger thing. So it will be like memory latency multiplied by the words per line. Okay, in our case, so words per, because the memory will be filling one word. So, welcome back. Let's start the session three, the second session of this workshop. So, let's start it with the associativity concepts. Okay. So, let's start it with associativity concepts that. So, let's So so now we are gonna introduce a new term actually, which is known as the set, okay, or the vase, okay. So so let's put that into our previous example where we were discussing the direct mapped cache. From onwards, where we will fit our new definition into that. So we had a 4-line cache, right? Direct map, if you are calling the direct map cache. Okay. So for this direct map cache, we observed that it had, like, for example, 4 words: 0, 1, 2, and 3, and all down towards in all the lines. Okay. So how we access those, you could say, lines was using index bits and then word offsets to access the individual words inside those lines. So in direct mapped cache, what happens is you have a single line in very single kind of a, you could say, location for a single memory address, right? Or for a single line. For example, if our address that falls into L0 will come only into this, right? In line 0. If it needs to, like if there is some other data in L0 and line 0, then it needs to evict the data, right? It throws away this data and the new data is updated in that line. So we say that we have fetched the new cache line, right? So now we are gonna say that these L zeros that we were calling the line 0, line 1, we are making and modifying a bit more, okay, because in the start we started off differently, and now, so let's say this line, not at L0, L2, or L3, we could say these lines as the set. Okay. So this was a set 0, this was a set 1, this was set 2, and this was set 3. Okay. So how can we now define this direct map cache? Okay. So we are defining now this direct map cache is that it has one line per set. Okay. One line per set. So whenever, for example, it selects set 0, there is only a single line in that set. There is no choice for that incoming data to be placed in some other location. Okay. So if a new lines come in from a different, you could say, memory location. For example, if we have memory, let's say that we have address 0 that comes to this line 0, right? So for example, this is 4 lines, and let's say there is address 16 that also comes to this line 0. So 0, 1, 2, and 3 memory addresses will be fetched to this, all 4 will be fetched into this line, right? Let's say we have now a request from address 16. Let's say that 16 also goes to the line 0 or set 0. Now we are calling it the set 0. So now issue is now the set 0 has only a single line in it, right? It has only this line, single line. If I could just color code a bit. So, so there is a single line. This is a single line here in set 0. So when the request from address 16 comes in, there is no choice for that address to actually go into some other ramification. That's why it is called a direct map. It every lines maps to directly one location in the cache, right? So what it does, it throws away its zeros data and comes in, right? Updates its tags, updates its valid bits, updates its data, right? We all saw this. So now so direct map cache is, you could say, it has one line per set. So if another request comes from another address for the same line, there is no option actually to place it there. Okay. So for that, we need to throw away the first one. And so let's say we have an option. Okay. So let's build that option. So let's say we have a cache which now has four sets. Let's say we it have four sets. Okay. In a similar fashion as our above example, set 0, set 1, set 2, set 3. Okay, let's see. But now, instead of one line per uh, set, it has now two lines per set. Okay, so what does it mean is it has now two lines. So this is a full-fledged line. For example, this is L0. For this is L1. Okay, so now it has two lines where valid, tag, and we could store the data as well. Okay, valid. So for now, just consider this. We will be changing this structure in a short while. So now each set has two lines. Okay. So now what happens is when now the data arrives at this set. Okay. So now it has two options actually. That is not fixed that it should go into the line 0 or line 1. Set is fixed. Okay. So set was also fixed in the case of directed map caches. Okay. Set was fixed. So address 0 should go to set 0. Okay. But the issue was that set 0 has only one line. Okay. This one. So that new data, if it is not the hit, it is going to replace the data, right? But for example, if we have two lines in this set 0, what would happen is, for example, the request comes from address 0, it goes into line 0 for set 0. And then for say, let's say the address 16 sends the request. Okay. And for the sake of example, let's assume that this address data should go into set 0. Okay, so set 0. But now we have the liberty actually of two lines here. So even L0 is being occupied here by different cache line, we can definitely put this 16 into set zero's second cache line. Okay. So in this way, I do not have to evict the first data, right? Now I have the option to put two cache lines in a single set. For example, in this example, set zero has two lines, and we could put the two lines into that. So what happens is now we are reducing number of misses again, right? Because we can accommodate more number of lines per set, so that we do not have to make a very fixed kind of place for a single cache, right? So this way, when we build this cache this way, say that it has two rows. Okay, this is a two-way set associative cache. Okay, so these are known as associative caches. Two-way set associative cache. So let's assume if each set has four lines, four ways, okay, then you would say that uh, this is just a four-way set associative, right? Eight-way, 16-way, or even we can build a fully set associative. So that will be like a very uh, uh, reverse of a directly mapped cache. That was exactly one line per set, right? So if we go into the opposite direction of a we go to the fully set associative. Which does mean, which means that all of the cache is just a single set. So for example, this is all of the cache is at zero, and then we have the ways inside it. Okay. So this really is the opposite of the directly mapped cache. In directly mapped cache, you have one line per set. So every cache line is a set itself, right? And while in fully set associative, full cache is a set, and all the cache lines or all the uh, lines in it are divided into you could say ways. So you should say that we are fully set associative. Okay, so all of these types of caches have their pros and cons. For example, direct map cache uses lesser hardware than other caches because there is more counter circuits and more kind of a comparisons in terms of comparing the lines within those sets and all that stuff. So it is more expensive in terms of that, right? So that's why we do not like suit as specific applications. Similarly, the free site associative have is like too much expensive because there are a lot of comparisons. So maybe that's why 4-way or 8-way associative caches are usually uh, are used mostly actually because they are a good compromise between the uh, increasing the increasing the hit rates and decreasing that hardware cost as well. So 4-way associative or the 8-way associative are the good ones. Uh, so let's so let me point out an issue here. So and then we'll come up with the solution of that as well. So by the way, not one, two issues. So let me just erase this and draw it a bit in in a way so that we could address. First, I'll present you the problem for the set associative caches now. With that problem, we not like seeing in other cache type. Okay, so for the directed map as in associative caches, in associative caches, this will be the issue. So let me just erase it and just build it again so that there's a cleaner version of it. So let's say we have a set associative cache. Let's say it has four sets. Okay, so this is set 0, this is set 1, this is set 2, this is set 3, and let's say each set has two lines. Okay, let's simplify this thing. So now each set has two lines. And then we know that it has data bits, it has bits, it has valid bits, right? So now the problem is when we arrive at the set zero, right? So for example, when we arrive at the set zero, let's say it has two ways. So these are the ways, okay? Way zero and way one. So every has way zero and way one. So now we are saying those ways. So set zero has way zero and way one. You actually both of these ways are filled, right? With the data. With the filled with valid data. So anybody could answer that question as well, or maybe you guys already know some of it. So we'll fill with valid data. I'll ask this question. So now another request comes in. We will simulate the requests as we did in the direct map cache section as well. So let's assume. So these both are filled, means these both are valid. They have some valid tags. Uh, okay. Let's say they both have like valid data in them. Uh, okay. So another address comes in and now it has a different tag. Okay. And it has to go to set zero because its address is like that. It needs to go to set zero. So let me. So my question on this is in which way it should go into way zero to way one because now it needs to flush out one of the ways to make its place right in direct map. So let's start the session on the coding side.